Then let's continue where we left off. So the first thing I want to do is structural approach. For example 1, what this means, it will get clear in a second. Example 1, and then MDPs, because so far we've seen this deterministic Markov decision process, and now then we want to make this a step to Markov decision processes and their associated concepts, and then the solution theory, which is fairly similar to the deterministic case, but still a little different. So the solution theory for MDPs. So where I want to start is essentially where we left off last time, when we applied the Bellman equation / dynamic programming algorithm to our example with this company. And before I tell you about the structural approach, that is after all important, let's briefly get back into it and think about what the example was. So the example was what I call a deterministic Markov decision process. So let's start now with the structural approach. Actually, I put my English notes now into the content folder. So there is now some stuff translated, and of course also a little bit different from the Schild stuff, because the Schild stuff doesn't do this step of stating that there is a Markov decision process, which you may or may not do, but I think for our purposes this is really helpful. So you can look it up there. I'm still working on the exemplary application for the second example, so there will be more. On the other hand, it's not really clear whether you ever need to study this really, because there's no exam on this. So let's go back to our example. So we had a deterministic Markov decision process. I changed a little bit in the conceptualization, which related to some discussion we had last time, and also how Schild does the next example, where actually there is no action at the final stage. So there are only now actions from 1 to t-1. I also changed the initial index from 0 to 1. This is more kind of a programming issue, but because what I'm doing here is part of a larger work project, and where I'm usually starting from 1, not 0, I've changed this now also to 1. It's really research-oriented teaching here, where the teaching really adapts to the research. So that's great. That's not confusing. It's research-oriented teaching. Forschungsorientierte Lehre. Yeah, good. So this was our DMDP, so a deterministic Markov decision process, as I call it. So what were these things? T were the number of decision epochs. So that were these investment periods of this company, and it was just a number. S was the state space, which were just the real numbers, so all numbers that you know, no vectors or anything, just numbers. The action space was the investment that could be done, was also just the real numbers. The rewards were so that was the capital stocks, stock values. The actions were the so the action space were the possible investment. The rewards were the net capital stocks. So remember there was this little formula, net capital stocks, which we will see in a second. And then our state variables from 1 to t are modeling the capital stocks. This might always appear a little bit redundant with this set big S and these capital stocks S1 to T, but it's not redundant because this big S says what kind of values these little S1 to T can take on, and this can in different cases, scenarios can be quite different. So it can also be, for example, vectors, or it can just be discrete cases if you just have a state space that just where there's just two states or something. So it's not redundant. A1 to t minus 1 are the investments that the company wants to make, and R1 to T are the net capital stocks. So maybe I should then call this values here. And F was the state and action dependent transition function, which was specified by the fact that if you have the state at time t and the action at time t, then the state at t plus 1, like this, was specified as st plus at. So that was the idea that when the company makes an investment, it on the next in the next decision epoch, it gains everything that it has invested. So highly successful investment. That was our transition function. G was the state and action dependent reward function that allocated to each state and action a reward, and this reward RT was defined as st minus a square t. So there was this reduction of the capital by the investment to the square. And as previously stated, one could also do that differently and have the directly subtract the investment and then add the square root of the investment, I guess. But that's how this tutorial example works. And then what so this for all decision epochs from 1 to t minus 1. Now there's a terminal reward function which is new, which accounts for the fact that there is no action in the last decision epoch, which makes sense from a model perspective, as we discussed last time. It doesn't change the calculations that we did last time, because if you remember, the value function was equal to S capital T, so was the identity function, and the investment action was actually 0, so you can also see that as there was no action. So, but one can also use this terminal reward function, and this is used later on in the case of the stochastic version, so we are using that here as well. And this just gives a state-dependent terminal rewards at the last decision epoch, and that was just defined as the identity function, so just as the state. And then the problem, so that was our process, our deterministic Markov decision process. And then the problem that we worked on was to maximize over actions 1 to t minus 1, which you can view as a list of actions in the product space of actions. So there are t minus 1 actions, so for example 9, and each of them is in the action space. So actually this sequence of action you can view as one as a list in the action space to the power of 9, which means in the product set of these actions spaces. And the aim was to maximize the cumulative reward, which that's still the typo, which is given by this plus, and this we didn't need earlier, but now we need it, plus the terminal reward, because of course this is also to be maximized by means of the action that is taken one decision epoch earlier. And this was subject to the transition function that we have above. For t from 1 to t minus 1, because then s big T is given and s1 no. So that was the problem. Takes some time to actually explain the problem already. And then what we did is that we used the Bellman equations / dynamic programming approach to explicitly compute the solutions in terms of optimal decision functions for t from, we did it for t, now we wouldn't have to do it anymore for t because that's given. And then we did it for t minus 1, t minus 2, maybe t minus 3, I don't think, maybe not, maybe that was the homework. And to t minus 2. We get the following results. So this just to remind you of what we did last time, but also as the beginning for the current session. So we evaluated with the Bellman equations, we evaluated the value functions. And we evaluate the optimal decision functions. Because after all, that's what we want to do with the whole thing. Optimal decision functions. And yeah, remember that the value function is defined as a function that takes in the state. Maybe let's write that like this. Takes in the state, returns a real number, and has a definition. Oops, has a definition that we are not looking up, or I'm not writing up now again, because we will see it in a second again. And the optimal decision function is the one that yields the largest reward and is basically maps states to actions. What is this? This doesn't look nice. st to vtst. Thing with the value function is that there are many for each time point t, and so there are for the optimal decision functions that return the optimal actions at each time point. So, and what were our results? So I've written this up now for t defined as 4. So then our small t runs from 1 to 3 to 4, and what we computed first, so we computed it backwards. So maybe I start writing it up backwards here. So we first had our value function 4 as 4, evaluated as just as 4. So last time this was big T. I'm just writing it up now so that you can see the order actually from 1. This is otherwise, yeah, one could also write it up backwards, but I want to, especially with the structural approach, yeah, it's also helpful to see it this way. Optimal decision function. Last time we computed a big T equals 0. Now we abolished the last action, so that doesn't exist. V3 as 3. We found 2 as 3 plus 1 over 4. And for the optimal action, we found that this is actually independent of the state and is given by 1/2. And we did this by maximizing these h functions and yeah, first writing down according to the Bellman equation what we have to do, and then maximizing with respect to action. For V2, we there's something we also did, plus 4. And again, this was independent of the state, and for
wasn't it minus 1/4?
That can be.
I think you got
No, I have the 1/2 minus 1/4, and that would be plus 1/4.
okay.
And finally 4 as 1. So this was somewhat the homework or whatever. But of course, this is just, I mean, these calculations, the exact results, I mean, at least from my perspective, they don't matter that much, because I'm not in this company and I don't want to make sure that they make money. I want to understand the framework, and whether it's 14/4 or 16/4. Well, that one can kürzen, but yeah. So see it more as how this actually, what kind of results you get. And as you see, you get these optimal decision functions, which are here independent of the state, and you get these optimal value functions. Now, as I said last time, or as I also see we have here now, if we have just 4 decision epochs, we are done. If we now would have another decision epoch, we would again go through this process of writing up the Bellman equation for the next time point, going backwards from, for example, 5. And then we would again have to do this maximization. Now, what is nice from an analytical perspective is if one can simplify proceedings by not having to do this maximization all the time. And this is really like a analytical mathematical approach. So if you have a computer and you have a complex problem, then you might want to do all these maximizations, but you don't have to do them like we did by thinking about it, but by just doing it in some a reasonable way on your computer, and then you don't have to worry. However, in these small examples, these structural solutions come up, and they are interesting and they are mathematically pleasing. And I want to at least give you the way to think about these structural solutions, because they are also they involve induction proofs usually, and induction, especially in the case where we have this recursion, where recursion of course just means that what's happening at v3 depends on v4, what's happening on v2 depends on v3, and so on, so that this temporal dependence, this is very close to induction, and I want to try show you and explain how these structural approaches work in this example. So the structural approach that I want to introduce now, this is typical mathematics, which is different from what you are used to in high school mathematics, or also what I have discussed so far, is where you have kind of a problem and then you have kind of a method, like we have the Bellman equations that you apply, and then you have a solution. The mathematical approach is you just guess a solution and then prove that it's correct. Yeah, so that's it's not constructive, but it's enough for mathematicians to be convinced that some solution is correct. Now, what is a guess for the value functions here? A guess would be that VTST is of the form alpha T ST plus beta T. Why? Well, if one looks at these forms here, one sees that there's for V4 there's S4, V3 there's S3, V2 there's S2, and V1 there's S1, and always these states are multiplied by some number. So this is what this alpha T means. So that's a number. Let's say it's a real number, and then there is something added. So here you can also view this as 0 being added, then 1/4 is added, 5/4 and 14/4 is added. Yeah, so a guess would be that in this problem the value function takes this general form. That's just a guess, and because somebody has worked it through, we can be confident that this is a good guess, and we don't have to worry whether in half an hour we will see that this was a bad guess. The other thing is the case of the optimal decision function, where a guess would be that this is just a real number independent of the state. And how is this guess motivated? Well, we have 1/2, we have 1, we have 3/2 numbers, so maybe that's a good guess. Now, what one then can do with such a guess is to prove that this guess actually holds, and also get explicit recursive formulas for these numbers. Yeah, of course, one thing is, okay, the value function takes this form, a number times the state plus another number, and the optimal decision function just takes a state independent number. But of course, it's a little bit more informative if for each time point we can compute actually these numbers that go into the value function and into the optimal decision function without having always to do this maximization step that we did last time, or these maximization steps that we did last time. The way to prove this, and this is also very much this is something that we will see a lot in these recursive schemes, is induction. Does anyone know what an induction proof or vollständige Induktion? Have you learned that in school, or there's a question? Or do you know that?
I know it, but
okay, so what is it?
You prove it like for one, for example, for one, and then you show that from n follows n plus one.
Exactly. So where do you know that from?
I did math courses.
You did math courses. That's good. Yeah, that's exactly the idea. So the rough idea is that, like you said, so that you use what is known, and we will see that in a second, a base case. That's the English term for Induktionsanfang. You start with a base case where for one time point in this case, or one decision epoch, or a general one instance of your sequence, you show that this holds, and then you go to a general scenario where you say, okay, I know it for some iteration t, because you always know that you know it for one because you've shown that in the base case. And from this general iteration counter t, you show that this holds for the next iteration counter. And because you have the base case, you can then develop the recursion based on this induction step proof. So these are these two things, the base case and the induction step, and they are and what they mean and how they look, we will now see. So the base case in our case is actually really simple. So we do the induction proof also backwards, because we want to use the Bellman equation for that. So we look at the case that t equals big T, and for this we have in our definition of the of our deterministic Markov decision process, we have GTST. No, actually we don't have that in. Sorry, this is from the Bellman equation theorem. So there, last time we had so that the value function big T is the maximization over the last step for the action. Now there is no action anymore, and actually in this case, if there is no action anymore, then it's directly identical. So the value function for the last time step is just identical to the terminal reward function. This is part of the Bellman equation setup, which we don't prove, so we don't have to do anything. This is just from the solution theory for deterministic Markov decision process. It follows that this is the case. And what we have from our definition now is that this is just ST, and this, so let's look that up again. So this is what we have here. So this is just in the definition of the problem. And this is, of course, of the form alpha t st plus beta t if we set alpha t to what? One, exactly. And beta big T to, yeah, exactly. So for one index small t, this structural approach that we propose here, that actually holds, and we have for this also the alpha t and the beta t, big T in this case. Now the induction step. So the induction step always starts with the assumption that actually this inductive property is fulfilled. In our case, it's the assumption that Vt plus 1 is of the form Vt plus 1 St plus 1 alpha t plus 1 St plus 1 plus beta t plus 1. So the way you can think about this is we are now actually looking at an arbitrary t, but of course you can also view it as that we are looking at t being big T minus 1. Then our assumption is already fulfilled, because then we are here in Vt, so big T, S big T, and we are back there. Yeah, and because we have at least this base case, we know that this is a valid assumption, so we can at least show it for the base case and T minus 1. But we want to do it more generally, so that also when t is gets smaller values, then we have our result. Now we go back to the Bellman equation and think about the value function. So the Bellman equation said that the value function at time point t is given by the maximization over action at time t of the current reward function, which is a function of action, plus the value function at the subsequent time point, which is of course a function of the state at the subsequent time point, but the state at the subsequent time point is a function of the current state and of course, and more importantly, the current action. Yeah, so that was Bellman equation as we enough brackets as we discussed it last time. Yeah, so this is the bracket for the function f, this is the bracket for the function bt plus 1, and this is the bracket for the maximization operation. So this is what we used last time all the time to maximize things. And now we assume here that this function is actually of this form alpha t plus 1 st plus 1 plus beta t plus 1. So we substitute that into our maximization problem. And we also substitute our reward function. Here, I guess we should write this is for t up to t minus 1. Because in the case of the last t, the big T, the determinant reward function of course applies. So our g function was the st minus a squared t. Is there a question? No. Now putting in our assumption, what we get is alpha, of course, alpha t plus 1, st plus 1. Now st plus 1 is given by fst at plus beta t plus 1. So what we did now is just that we substituted our reward function, and we substituted our assumption for the value function at t plus 1. Now finally we can also substitute the state transition function, so we get max at a st minus a squared t plus alpha t plus 1, and the transition function was st plus at plus beta t plus 1. So this is now if we just substitute into the Bellman equation the definition of the deterministic Markov decision process, so the reward function, the transition function, and our assumption that the value function at t plus 1 is given by this structural form. Now we can solve this maximization problem like we did earlier. So we can again define this kind of helper function h by just the content of this maximization thing here. So to say that h of at is st minus a squared t plus alpha t plus 1 st plus, I multiply it out, then we don't have to worry about the brackets. So we have alpha t plus 1 times st plus alpha t plus 1 times at plus beta t plus 1. And we want to maximize this, and we did that last time already a number of times. So we compute the first derivative, which with respect to a, which evaluates to what?
Minus 2 at plus st plus a alpha t plus 1.
A alpha t plus 1 or alpha t plus 1?
Alpha t plus 1.
Yeah, exactly. Plus
alpha t plus 1.
Yet another alpha t plus 1? No.
Oh no, because yeah, that was good. Okay.
So R, yeah, exactly. R is only here, A is only here and here. So all the other things go away, and alpha t plus 1 is there. And the second derivative is what? Minus 2, like it was all the time, which is good because then we know if we have the first derivative equals to 0, then it's definitely a maximum because the second derivative is negative. So we can use this and set it to 0. So we get minus this optimal the optimal action plus alpha t plus 1 equals 0. So we see quite easily that the optimal a is 1/2, because we need to divide this. This is negative if it's on the other side. 1/2 alpha t plus 1. Now we have already seen this. So alpha t plus 1 is a number, and 1/2 a number is also a number. And if we define our gamma t in our structural approach to be 1/2 alpha t plus 1, then we already have a method to compute the optimal actions based on the base case of alpha. Now what we also want to look at is the optimal value function. So if we substitute our this solution into this, because we now found the optimal, so the argument that maximizes this, the optimal action, then we get st minus 1/2 alpha t plus 1 square plus alpha t plus 1 st plus 1/2 alpha t plus 1 plus beta t plus 1. And yeah, this we can essentially just rearrange to make it of the form of our structural proposal for the value function. So just by rearranging, we get st here, we get 1/4 alpha t plus 1 square plus alpha t plus 1 st plus 1/2 alpha t plus 1 square plus beta t plus 1. So we have an s here and we have an s here. So we can write 1 plus, or the other way around, doesn't really matter, alpha t plus 1 plus 1 st. So then we get alpha t plus 1, we get this term, and plus 1 we get this term, plus 1/4 alpha t plus 1 square plus beta t plus 1. So this was 1/2 alpha t plus 1 square minus 1/4 alpha t plus 1 square, which yields 1/4 alpha t plus 1 square plus plus beta t plus 1. And then if we now say, okay, we call this alpha t, so this number given by alpha t plus 1 plus 1, we call this alpha t, and we call this number beta t, which is then given by 1/4 alpha square t plus 1 plus beta t plus 1, then we're actually done. So we now have our vt st in the form alpha t st plus beta t, and we have our optimal dt in the form gamma t, which is 1/2 alpha t plus 1. So that was a lot of t+1 and t, and alpha and beta and gamma, and r and b. But the nice thing about this is that one now has these formulas for this example. One has these formulas and can just basically put in the initial alpha big T and beta big T, and then compute the value function and the optimal action without having at each step to do the maximization that we did last time. One can actually, in this example, and you find this in the shield, one can even spin this further and find explicit solutions in terms of the time points for the coefficients here, which is then even better, because then you don't, if you compute it on a computer or in your head or on paper, you don't even have to do a recursion, but you have just a formula that for a given time point, you can just compute this. So this shows how one can basically avoid having to do what we did last time all the time in these kind of analytical treatments of these sequential decision problems by using induction. Yeah, so that's the crucial thing here. Really, of course, it's helpful if you have your own experiment and you start thinking about what you can do and what an optimal solution would be. And if your experiment is really simple, which most cognitive neuroscience experiments actually are, then you might be able to find an optimal solution and then can check whether humans perform optimally or how they can perform well without actually knowing all of this theory. Okay, so this was kind of demonstrating the structural approach. Are there questions about this? Okay.
How do you get the explicit solution from this step? And if the explicit solution is a function of time steps, it has to be value function?
So the explicit, actually I didn't prepare that. So the explicit solution then look roughly something like, so I'm doing it really roughly. So it has kind of this form, something like this, so that it's not like this, but the idea is like this, so that you have a time index, and on the right hand side you don't have to compute something based on t+1, but you have an explicit function of the time index essentially plus some constant maybe, and maybe start at 1 here. So here you would just have the sum of the time steps. So this is kind of the form that these explicit or closed form solutions take, where you don't have to do a recursion even. Yeah, because for what we've seen now for the structured solution, this you still need to do a recursion. So you still need to, if you want to have it on time point small t, you need to know what's happening on t+1. And you have to
also make assumptions about the values of alpha and beta and
to get to this, no, I think it's essentially just a reformulation of this. So you basically substitute things. So you start with 1 and 0, and then you substitute, and then you reformulate this. So you don't need an induction again, I think. But as I didn't calculate it myself. So I think in the shield it's also very brief. So if one would, so this is why I haven't prepared it, because it needs a little bit of effort to actually show that. But then, of course, it's an even nicer result because you don't need any recursion anymore. Okay, other questions? No. Okay, we don't have to take a break, but I need to get my nose free of schnodder. So I'll be back in a second to continue. Good. So then in the last bit of this session, we now make a cut and make the step to the stochastic problem. So what we've seen so far is all the mechanics and all the complicated stuff that is involved in sequential decision making optimization, and which is involved in kind of formulating Bellman equation using dynamic programming to do these maximizations. What wasn't involved at all is uncertainty, and in decision making under real life conditions, of course, there are various forms of uncertainty. A very immediate form of uncertainty that we are also familiar with from what we talked about in decision neuroscience is, of course, perceptual uncertainty, which actually, if one does it formally, corresponds or is can nicely be formulated as state uncertainty, given some observations. This is not what we are dealing with here, and what Markov decision processes where the uncertainty comes in. It's also not reward uncertainty, so it's different from the lottery case where you choose an option and then you might get an outcome of 1 or 0 with a certain probability. This is also not the ballpark of standard Markov decision process theory. But what is the ballpark of standard Markov decision process theory is state transition uncertainty. So where previously we've had this transition function f that just said if this state is at time t and this action is taken, then at the next time point we will be in that state. This is generalized in the standard MDP case to transition probability. And what I want to do now is to first write down the standard MDP, which we will then later on use to tackle this problem of the Gambler, whose capital was always dependent, so whose state was always dependent on some random influence. So I want to state this general problem and then explain some parts of it, which I think, or at least from my studying this, need some attention, and it's good to be aware of it if one then wants to apply again the idea of dynamic programming. So we are now actually dealing with a real MDP, not what I called a deterministic Markov decision process previously, but a real Markov decision process. However, it has at least two features that make it not completely general. So we consider a time invariant and a finite horizon. Markov decision process. And like before for the deterministic case, I'm talking about process if I mean the problem specification without the maximization that is to be done. So basically just describing the dynamics of the problem. And then I'm talking about a Markov decision problem if it's clearly identified what should be maximized by the decision maker. So a time invariant finite horizon Markov decision process is again a tuple, and of course it doesn't look that different from what we've seen before. Otherwise there would have been no sense to talk about what we discussed previously. Just writing it up first, and then I'll tell you what these things are. So what are these things? T, again, is just the number of decision epochs. And the important thing is that T is smaller than infinity. So T is just a natural number that is not infinite. Hence, we have a finite time horizon. And this is actually important because there's a lot of theory also dealing with an infinite time horizon. And infinite time horizons are interesting in the sense that they approximate very long time horizons. And then things get a little bit different. And yeah, especially if you're thinking about these, all the stuff that is in cognitive neuroscience that relates to discounting, this is all related to infinite horizon problems, which approximate very long time horizons. I like the finite horizon problem more, and I think it's of more relevance for decision neuroscience, because after all, your experiment will always be over, and I don't know whether you know, but unfortunately your life will also be over at one point. So as a human, you have a finite time horizon. Yeah.
Just because we were discussing about this yesterday, and I think psychologically for me it would make more sense if we would perceive it like we would be more interested in infinite horizon, because we don't know when things end, and
That's a different issue. So yeah, I mean, one thing is that you know that something ends. The other thing is that you have uncertainty about the endpoint. And another thing is that you think it's never ending. And so especially if you're trying to tackle, from my perspective, when you're trying to tackle decision neuroscience experiments, then as an experimenter, you have a good idea of when it's ending. Of course, you can then, I mean, it's an interesting research question after all. I mean, you can look whether humans behave more as whether they consider an infinite, behave optimally, but under the assumption that there's an infinite time horizon or there's a finite time horizon. It's an interesting research question. The other thing is that things get a little bit tricky if you're thinking about optimal stopping things. So if you are yourself ending something, then then this MDP framework still applies, but it comes in a different shape in terms of optimal stopping problems. So this the time horizon, yeah, has many facets, and here I'm just saying it is known that it ends, and the endpoint is known. Yeah, because then it takes, the whole theory takes a specific form. S is the state space. That's like before. So this is a set of numbers. A is the action space. Again, a set of numbers, sometimes also vectors, but usually numbers, depends on what you're modeling. R is the reward space. And now our S1 to T are our state variables. And one thing is very important now, in contrast to the deterministic Markov decision process that we discussed previously, the state variables are now really random variables. So they intuitively they take on values randomly. Yeah, so they model a stochastic aspect, and for these there is actually given a sequence of actions, there is a distribution defined on over, so there's a joint distribution defined over all of them. will tell you in a second what that is, this joint distribution, but they are now random entities. Yeah, so they don't take on numbers deterministically like previously. If you remember again, if you think about the capital stock of this company, of course, what the capital stock is depends on the action, but the action was deterministic. The initial capital stock was deterministic, and then the next capital stock was just given by the sum of the capital stock and the action. So there was no randomness involved. Here, randomness is involved, and we will see in a second how this randomness unfolds. Some random variables, and these are random variables, random state variables, but they are, most important thing is that they are random variables. In a mathematics sense, of course, have you studied random variables? Do you know what random variables are mathematically? Because mathematically, random variables are something different from what one intuitively thinks. So mathematically, they are also functions, but that's a different issue. And we are using this applied idea of random variables here, so that they are variables that take on random values. Our action variables, A, T, this one. And that's also important. Action variables, they are not random variables, at least in the standard theory of Markov decision processes. These are the variables for which you want to find values that maximize, in the end, again, your expected cumulative reward. It's somewhat weird with actions in cognitive neuroscience, because actions in cognitive neuroscience are usually the actions done by the participant, and to account when you have a model and you want to account for some randomness in your model, so that the participant might not always exactly behave like your model predicts. And you allow for some, let's say, observation noise or noise in the decision maker, then they actually become random variables in the context of cognitive neuroscience. However, we are currently not talking about cognitive neuroscience, but about time invariant finite horizon Markov decision processes. And in this theory, they are not random variables. So they are just something, they are just variables, like algebraic variables, that you want to optimize with respect to. Then the reward variables are somewhat tricky. I mean, everything is tricky, but these are the reward variables. And the reward variables actually become random variables because they depend on the state variables, as we will see in a second. So let me postpone that for a minute. So we are up to here. So what is PS1? That's the initial distribution over states. So that's a probability distribution over S1, so over the random variable S1. That needs to be specified, otherwise the problem cannot be simulated or solved. Of course, it's in some way analogous to the thing that you knew as 1, although not quite. More important is actually this action-dependent state conditional state transition distribution. So that's really one core feature of the Markov decision process theory. So, and it took me a long time to realize that this transition probability, state transition probability distribution is actually action dependent and state conditional. So this is why I'm writing that up all the time. So what do I mean by that, and how can you envision that? So let's make a simple example. So assume that we have a state space with just 3 states. Yeah, 1, 2, 3. So there are 3 possible states. What is then this PAT ST plus 1 ST? Now, what this encodes is, we also need an action space, of course. Let's assume there are just 2 actions, 1 and 2. What this thing here encodes is for each action, AT being some action, the probability that the state variable at ST plus 1 takes on the value, let's call that I, given that the state at time t is j. That still might look fairly abstract. It gets clearer if we actually write something up like that. So we first have to, maybe we call that k. These things are really, so these state transition probability distributions, they really are the meat of a Markov decision process, and they can, especially if things are non-parametric, so if you have discrete sets of states and discrete sets of actions, they can become quite large in terms of the information they encode and what you have to write up. So what do I mean by this? So in our case, we have 2 actions. So we can think about the action at time point t being 1, yeah, because that's a possible action. And then at time t, the state can also be 1, yeah. At time t plus 1, the state can be 1, yeah. It can also be 2, and it can also be 3, all for the case that actually the state at time t is, the state at time t is 1, and the action at time t is 1. Yeah. And what this means is that this should be a probability distribution. So you know that probabilities in this discrete sense, they need to sum to 1. So maybe let's say the probability that state at t plus 1 is 1, given that state at time t is 1 and action is 1, is 0.2. The probability that the state at t plus 1 is 2, and the state at t is 1 and action at t is 1 is 0.5. And hence, what do we have here? Here. So the probability that st plus 1 equals 3 given st1 and at1 is 0.3. Now we only considered one thing, namely that the state is 1. That means to fully specify in this very small case scenario where we have just 3 state values and 2 action values, we need to specify further things. Namely, we need to specify the same thing again for st being 2. And for st being 3. Again for the thing that a equals 1. So I'm not writing everything up as you see. I'm just, so you have to imagine the p and the st plus 1 being 1, 2, 3. And once we have specified these probabilities here, now I'm writing everything up anyway. Let's do that. 1. That's the nice thing about doing things on a computer, then you can just copy and paste. I mean in digital version. So 1, 2, 3 for st plus 1. And of course these probabilities can be different, they just need to be probability distributions. So here we could have, for example, 0.4, 0.1 and 0.5. And once we have done all of this, we have to copy and paste this here or somewhere else and write the whole thing up for the second action, yeah? So that we know, and this is how we have to specify the problem, that we know for each possible action at time t and each possible state at time t, what the probability is that the state at t plus 1 is one of the possible states. Yeah.
What is the difference between dependent and conditional?
Yeah, that's a very good question. The difference is actually subtle. So this is, let me first maybe erase this now, because I just want to show you how complex these state transition probabilities can get, even in the case of very few states and very few actions. Now I have a bigger. Well, this will take forever. Yeah, but then we can't go on here. Maybe if I put it on my finger. So what is the difference between conditional and dependent? The reason why I'm making this difference is basically just to indicate that actions are not random variables. And shouldn't have written this up. I scroll after all. So and p as 1 we are given, and this holds for t1 to t minus 1. The thing is, you often find this actually also in books. You find this written as follows, STAT, which also of course means the same thing, that the state at t plus 1 is dependent on the state at time t and the action at time t. Now when I see this, when I see these conditional statements, then I always think of everything that is behind this as a random variable. And as I said, because only then these things make sense. So if you remember the law of conditional probability, or the definition of conditional probability, you have a joint of two random variables and you divide by py. That means that what you have here behind the conditional statement, there is a joint distribution with respect to that. So this is random variable has some probability associated with it. Now these ATs, you don't define a probability for them in the MDP literature. So this is why I don't like to write them here, but to make sure that they are included, because as I've shown you above, the state transition probability depends on the action. I include them here. Yeah. This is why I call this thing action dependent and state conditional. So action dependent and state conditional, but not action conditional. If you again use the notion of pxy times py equals the joint of x and y, if you use this logic, then you actually also see here that you define the joint distribution of states depending on the actions from 1 to t minus 1 by the factorization so by the product of p let's see whether that works with my indices. PS, and then this must be T 1 to T minus 1. Yeah. So that actually implicitly in the definition of the Markov decision process, there is a definition of the joint probability, the marginal joint probability distribution over all state variables. That's there, that's action dependent, but there is no definition about the marginal probability distribution of the actions. That's just not there. It's just the transition probability and the initial state probability that is there. So this is maybe a little bit more advanced at this point, but it's actually quite crucial in realizing what the problems are when actually solving Markov decision processes, because the problem is really that you're not given the probability distributions that you actually need to solve it, and you have to first basically figure out the probability distributions and work with the probability distributions that you're given. So maybe let me finish the specification of this, and then I'm afraid the rest you will have to watch on Christmas Eve. No, maybe not Christmas Eve, because I will not have done it, but you can watch it on New Year's Eve and the 1st of January, because I think I will do it next week, how this is actually applied. But first let me finish the thing here. So we have now specified this, and then we also have, like previously, a reward function, which as previously takes states and actions and maps them onto rewards. The problem is now that the states are random, and although this is of course a function, there's no randomness involved, but what you do is that you transform a random variable, namely st, through a deterministic thing, and then what comes out is again a random variable. So this is why the problem of in terms of the Markov decision process, the real Markov decision process, is not to maximize, maybe I knew that quickly here, the problem is not to maximize the cumulative sum of rewards, as we have seen before, but, and that's the big problem, the expected cumulative sum. Yeah. So here you're not able to compute the cumulative sum directly, but you can only say something about the cumulative sum of the rewards in terms of its expectation, because things are random now, and the only thing that the best thing that you can do from a mathematical perspective is to choose your actions in such a way that on average, so over many repeats of this process, you're doing a good job. And this is where the expectations come in. The GT is finally the terminal reward, which takes the terminal state and maps it onto the terminal reward. And of course, this is also random, and you want to maximize, of course, you want to maximize this, which also includes the terminal reward. I think I will leave it at that. I have, so already in the notes, there's more on these expected values, because they are really, so if you compare to the deterministic Markov decision process, everything is the same except for these probability distribution over states and the expected values. So they need extra care when dealing with them. They then also show up in the Bellman equation, where you have the expected value of the value function at the next time point. And so computing these expected values, that's the only step that you need to do if you want to progress from deterministic Markov decision process to real Markov decision processes. But this I will do in the comfort of my own home with a nice cup of coffee next to me and a computer to which I will talk, and no questions that can be asked. Although actually there are these things where I could also do a call, as they call it now, and then people can ask questions by chatting. Good. So this is where I stop this, but this is, and maybe just as a pointer into the real future. So the real future, of course, is also non-Markov decision processes, but partially Markov decision processes where the states are unobserved because you have perceptual uncertainty, and then you have, in addition, you have a distribution over a conditional distribution over observations given states. And then things become even more interesting, because they become more like the real world, because you not really know what's going on outside. You just can infer what's going on. And then, of course, to behave in a good way and under such conditions is even more tricky, but somehow humans can do it. So this is why this whole framework is interesting. Good. More videos will follow. You don't have to watch them to pass the thing. You need to prepare your presentations. Yeah? Questions? No. And you're finally done with